Okay, so today's going to be the first day of electricity, and before I begin, I just want to let you know that obviously you've seen the assignment in the Google Classroom, this electricity voltage Google Doc. If you click on that to create your own copy, you just go up to File and then make a copy, and then you'll be able to have a copy that you can edit and put in answers as we go along. Okay. And another thing is also there are two previous videos, okay, how electricity works, and then voltage explained. They go into a little bit more detail with their animations that I could do. So after you watch those two, okay, come back and watch this video. All right, so let's just jump right into it. So, electricity, day one. So, at the atomic level, electricity depends on mainly the electrons, but also want you to be aware that in the nucleus, that's the center of the atom, there are protons and neutrons. Okay, and those two things tell us what kind of element it is. So, for example, this right here with 3 protons, this would be lithium. And the electrons orbit outside the nucleus, and those are the particles that can actually move to create electricity. Okay, conductors and insulators. So, conductors allow electricity to pass through them. Okay, so some examples are copper, gold, and even graphite. So the lead in your pencil, that can actually conduct electricity. Pretty much almost all metals are in this category. Insulators. Insulators block electricity from passing through them. So some examples would be rubber, plastic, glass, or wood. Now, one thing to keep in mind though is that conductors, they're not perfect conductors. So there's going to be some resistance. And with insulators, if you increase the voltage enough, you can get electricity to pass through them. So they're not 100% conductors, they're not 100% insulators. So circuits. So circuits can either be on or off. And so you can see in the closed circuit, the electricity can actually flow from one side of the battery to the other. In an open circuit, it's off because the electricity is blocked. Okay, there's no continuous path for the electrons to take. Okay, so I mentioned voltage earlier, and voltage is what pushes electrons around a circuit. Okay, so you can think of it kind of like pressure. High voltage means that there's a lot of pressure causing more current. Low voltage means that there's low pressure causing little current. So obviously high voltage would be more dangerous than low voltage. Okay, and we measure voltage in units called volts. And if you're wondering, it was named after an Italian scientist, Alessandro Volta. He made the first battery back in the 1800s. So just a little reminder, if you want to get a unit, you can name it after yourself if you discover something. So some common voltages. Okay, so first, nerve cells. So you might be surprised to learn that, yeah, our bodies kind of function on electrical pulses. So this is why electricity can be so dangerous for the human body because it actually interrupts those signals and it can overpower them very easily. You can see that the nerve cells operate on a very, very low voltage. 75, that's the Greek letter mu, stands for microvolts. So that's 75 millionths of a volt. Okay. Next, I include this. Some of you may have done this in a science experiment before, but a lemon battery, if you take a lemon or really anything that's salty or acidic, like a pickle would work too, I bet. Um, one side you put something that's copper, one side you put something that's zinc, and you actually have a very rudimentary battery. And because of those two metals that were chosen, copper and zinc, the voltage is 0.9 volts, so a little bit less than 1 volt. That's why in this picture it had needed 4 of them to power one LED. Okay. A AAA battery, those are probably like the smallest, thinnest batteries that you might deal with, say in a remote control. So those are actually at 1.5 volts. Okay. Now, obviously, you have other size batteries. So, what about the D battery? D batteries are the large ones. You might see them in large flashlights. Okay. those actually have a voltage of 1.5 volts. And you might be saying, well, if a AAA has 1.5 and a D has 1.5, why do you have different batteries? And the reason behind that is how long they last. So a D, you could theoretically replace D batteries with AAAs, and they would last for a very short amount of time. Um, the only difference between these two batteries is how much of the material and electrolyte they have in them. So the reason that they're 1.5 volts is because they use the same materials. So zinc and manganese dioxide. Um, and there is an alkaline, that's why they're called alkaline batteries. It's an alkaline electrolyte in between those two metals. So this just has more of those metals and electrolyte, so it'll last a lot longer. Okay, next up, a USB charger. So you guys have these for your phones, any other kind of portable electronic device. And those come in at only about 5 volts. Okay, so that's why when you plug something into your laptop, when you plug something into uh, one of these ports, you don't really have to worry about being electrocuted. It's very low voltage. And if we do get back into school, when we do our project on the LED sign, we'll be using a voltage of 5 volts. Okay. Next, a car battery. Now, it might surprise you to learn that a car battery is not actually that much higher in voltage. It's only 12 volts. Um, and the reason that they're so big is because there needs to be a lot of electrolyte. There needs to be a lot of the uh, lead plates. That's why they're called lead acid batteries. The acid is the electrolyte. Um, so yeah, these have to be able to provide a lot of current, even though the voltage is very low. Now a wall outlet, and I put in parentheses US here, because in other countries they might have a different voltage. In the US we have 120 volts. In Europe they actually usually have around 240 volts. So you can see there's a big step up from a car battery to a wall outlet. With a car battery, you don't have to worry about being electrocuted with a car battery. Okay, so you could theoretically just touch both of these terminals and you'd be fine. You wouldn't feel anything. Okay, with a wall outlet, that's very different. So that's why you really have to be careful. You don't stick anything in there that's not a plug. Okay, and you want to make sure all of your cords aren't frayed or have any exposed wires. And I thought I would include an electric eel. Okay, so these animals can actually produce a jolt of up to 600 volts, and they use that to stun their prey. Um, Not quite kill them, but you can stun them so they can eat it very easily. Okay, so some more voltages. So at the electric chair, um, little history behind this. The first electric chair was actually here in New York State, in a Sing Sing prison down in Ossining, and they used a voltage of 1,700 to 2,000 volts, and they came up with that number kind of through trial and error. Um, so these aren't actually used anymore. There are a few states that allow prisoners can choose their form of execution, but none of uh, none of the U.S. uses this as their primary mode anymore. Okay, street power lines. So these are the lines you see at the top of telephone poles. Okay, those are around 4 kilovolts. So just like a kilometer is 1,000 meters, a kilogram is 1,000 grams, a kilovolt is 1,000 volts. So this is why when you see people working on these lines, they have to be very, very careful. Okay? If you get electrocuted by one of these lines, say if they're down in the road, it could very easily kill you. Now, high voltage transmission lines, these are the ones that you see kind of cutting through fields and woods. They're usually very, very tall, made of metal. Um, and the reason that they're so tall is because they want to keep them away from the ground as much as possible, because they don't want anything accidentally touching one of these lines. Those transmission lines, those are 70 kilovolts or 70,000 volts. Okay, so you have to be very specialized in order to work on any of these. And lastly, lightning bolt. So a lightning bolt is between 100, if you're wondering, that's megavolts, and 1 gigavolt. So 100 megavolts to 1 gigavolt. And that number is 100 million volts to 1 billion volts. And at this point, some of you might be wondering, well, if it's so high, how can some people survive being hit by lightning? Okay. And the answer to that is the amount of time. So with a lightning bolt, you get hit, it's over, it stops. So it can easily stop a heart, but it's not going to 100% kill someone. Okay. So with these transmission lines, that's not the case. Okay. If you get electrocuted by one of these, it's going to continue electrocuting you. So I actually have a little video that I want to show you. So here we can see the branch. It's actually touching two different power lines. You can see it's starting to steam is being released from, and there goes the arc. So if we watch this one more time, I want to pause it at one point. So now you can see some of the steam escaping. Okay. So even though it's made of wood, the electricity can still pass through it because the voltage is high enough. Okay. And what's happening is it's heating up that stick, and all of the moisture and sap that's in that stick is being turned into steam and it's being released that way. And as soon as all of that is used up, it can increase in voltage. I'm not voltage. It can increase in temperature very quickly, and then you get this arc. Okay, and the only reason that it stops is because a circuit breaker must have tripped. Otherwise, it would have continued to go. So that's really. I want to give you some insight into, what's low voltage, what's high voltage, what's safe, what's not. So after you're done with this, there is a little quiz. It says Electricity Day 1 quiz, also in the classroom assignment. So you can just click on that, fill in all of the answers, and we'll pick this up in the next lesson.